Hello, our video today is going to be on simplifying and using the properties of rational exponents, but our focus is going to be on numerical bases. So we're going to remind ourselves on how we can simplify just a radical. We go back to those factor trees. It's any two numbers that multiply to 80. So maybe you do 4 and 20. I'm going to do 8 and 10. It doesn't matter. Maybe whatever you choose, just as long as they multiply to 80. 2 and 4, 2 and 2, 2 and 5. So when I look over here, I see that my radical, it is a cube root, which means I need groups of 3. So I have a group of 3 2's right here. That's going to go to the outside. But there's some leftover numbers here. Those are going to stay inside of the radical. It is still a cube root. When you have more than one number on the inside or more than one number on the outside, they get multiplied together. So this reduces down to 2 cube root 10. We go to number 2. I see this 6th root right here. So now I'm looking for groups of 6. I start to break this down, and I realize I'm not going to have 6 groups of anything. So if we look at this, this is 3 cubed. Well, I need groups of 6. I have 3. Those numbers, though, can reduce down. Both of those numbers are divisible by 3. So this is the square root of 3 to the first power, and we traditionally would just write this as the square root of 3. Now, if that doesn't make sense to you, just remind yourself that a radical is just a fractional exponent. So at this spot right here, think about it as 3. The numerator is the exponent. The denominator is the root. Well, that's a fractional exponent of 3 over 6, which is 1/2, when turned back into radical form, is just the square root of 3. All right, we get to number 3. I have a negative 64 to the 3/5 power. So I have a number base, but I don't have a radical. I have a fractional exponent. It's really important to remember what those fractional exponents mean. The numerator is the power, the denominator is the root. So this is going to be the 5th root, or a radical 5. My numerator is the power. Now it's this entire quantity raised to the 3rd power. So I'm actually going to have 3 negatives, which means I have a negative answer. That's going to become really important. Paying attention to those positive negatives. I break down 64. Again, you can go to your factor tree however you need to do it, but I find that 64 is 2 to the 6th power when I break it down. So this is a negative 2 to the 6th power to the 3/5. I now have a power to a power. When I have a power to a power, I multiply. So if we remember, 6 times 3 is 18, and then 18 divided by 5. We already know that our answer is negative. We established that in the first step. So this is a negative 2 to the 18/5 power. The negative is not going to go on the inside of the radical. The exponent is only to the number directly to the left. We have evaluated the negative, so it's outside the parentheses. So this is a negative 5th root of 2 to the 18th. Again, we go back to our root. We need 5, and we have 18. That tells me that I can make 3 groups. 3 groups of 5 account for 15 of the 18, which means that there are 3 left over on the inside. So negative 2 cubed gives me a negative 8, 5th root of 8. We go to number 4, same thing, we evaluate, kind of look at that exponent. The 2 is my power. I see that I have a negative 64 all in parentheses, so I have 2 negatives, meaning that my answer is going to be positive. So right now, I don't have to worry about my negative anymore. It's going to disappear. It's a negative times a negative, positive answer. And that 5 is going to be the radical or the root. So a negative 2 to the 6th power to the 2/5. Same thing, we have a power to a power, so we're going to multiply. We already established that our answer is going to be positive, so this is just a positive 2. 6 times 2 is 12/5. The 5th root of 2 to the 12th power. I need 5 and I have 12. So I can make two groups. 2 groups of 5 are accounting for 10 of the 12, which means that there are 2 left. So 2 squared is 4, 5th root of 4. Now this is not always going to happen. We see it happening on these couple examples where the same numbers on the inside and outside. That is not what normally happens. It's just a coincidence. It's actually going to happen in the next one too. So we look at number 5. We see our base of 9. With our number bases, we rewrite in those lowest terms. Again, if you need to use a factor tree, go ahead. Otherwise, I know that 9 is 3 squared. So think back to that warm-up where we did all those factor trees. Same thing, we have a power to a power, which means we're multiplying. 2 times 3 is 6. 6 over 4, we reduce that down to 3/2. So this is the 2nd root of 3 cubed. I need 2 in a group and I have 3. That means I can pull one group out and I have one group left. Notice I didn't write the 2. We know square roots are 2nd roots. I didn't write the 1 because I know it's that assumed value of 1. If you want to, you can. You just don't have to. All right, so that was just focusing on those number bases and how to simplify them. Now we're applying the properties of radicals. Just like we talked about with variable bases, it's about looking for something that they have in common. So if I look at number 1, they have the same root. So I'm going to go ahead and put them underneath the same root. You have options here. You can go ahead and multiply the 18 times 15 together and get this big number. But when it comes to number bases, we're always looking for the groups. So this would just be my next step in the factor tree. So I'm not going to multiply them together. I'm going to keep them separate and create one big tree with them. So 18 is 6 times 3, 3 times 2. I break down 15, 5 times 3. I need groups of 3, and I have 1, 2, 3 3s. So the 3 goes to the outside. I have these leftover numbers. Don't forget that this is a cube root. And then 2 times 5 is going to give us a 10 on the inside. And we reviewed in the previous section that we multiply those numbers. When I go to number 2, I see that they're not the same root, but we're always looking for something that they have in common. What I do notice is that they both have a base of 81. So in this case, they have the same base. So I'm like, okay, I have the same base, but how am I going to put them together? I remember that if I'm stuck, I switch form. So right now I'm in radical form. Oops, that's an 81. And then 81 to the 1/2 power. I quickly notice that I'm multiplying the same base, which means I'm going to be adding, keep on forgetting that one, adding the exponent. So 1/4 plus 1/2 is going to give me 81 to the 3/4 power. Now you think that we're almost done, and this is where number bases can be a little bit more difficult than variable bases, is I'm not done because my number base should always be broken down into smallest terms. So if I'm breaking down that 81, 9 and 9, 3 and 3, 3 and 3. So I'm going to rewrite this 81 as 3 to the 4th power. Power to a power, we multiply. 3 times 4 is 12. 12 divided by 4 is 3. This is 3 cubed. That's not a fractional exponent, so there's no radical. I just evaluate in my calculator 3 cubed. 3 times 3 is 9. 9 times 3 is 27. So we're not always going to have fractional exponents. We're not always going to have radicals. Different problems are going to take us different directions. So number 3, again, what do they have in common? As I'm looking through, what they share is the same base. As I look closer, I realize I have the same problem I did in number 2. There's no immediate way for me to put them together, so I switch forms, and when I switch forms, I can quickly see, oh, I'm dividing like bases. Therefore, I'm going to subtract the exponents. So 1/2 minus 1/4, which is going to leave me with 7 to the 1/4 power. I do have a fractional exponent, which means I'm going to go ahead and switch it from a fractional exponent to a radical. So you're going to apply all the properties just like we've been doing. Now we're going to be working on rationalizing the denominator. Remember, rationalizing the denominator is getting rid of the radical on the bottom, just like with the variable. So when I see the fraction, I'm going to take the 5th root, I'm going to break it down into 2 parts. Now there is a long way and there's a short way to do this. I see that I need 5 and I only have 1. That means I'm missing 4. So I could rationalize by multiplying the top and bottom by those 4 missing 4s. That's going to give you really large numbers. It's going to make it really difficult. So I'm not going to do it this way. Could you? 100%. Instead, I'm going to look at the fact that when I separate this, that base or the denominator of my fraction is a 4. I'm going to rewrite it instead of 4 as 2 squared. So you notice everything is about getting those number bases down to lowest terms. So that makes it a little bit easier. I need 5 and I have 2. Now I'm only missing 3 of them to rationalize. So I multiply the top and bottom. Oops. Look at that. I wasn't even looking. This is the 5th root. By that missing 2 cubed. Again, I need 5. I have 2. I rationalize with my 3 missing pieces. Both of these are 5th roots. That means I can put them together. So this is the 5th root. They are inside, so 3 times 2 cubed. Well, 2 cubed is 8. And that creates my perfect pair, not my perfect pair, my perfect group of 5 2's, which means the 2's go to the outside. 3 times 8 is going to make the numerator the 5th root of 24 all over 2. Now you may be thinking, oh, 24 divided by 2, that becomes 12. No, because with radicals, it's about location, location, location. 24 is inside the radical, 2 is outside the radical. So those numbers are not in the same spot. They do not get reduced down. All right, number 2, we look about this the same way. I have 2 over the 6th root of 81. I need 6, I have 1. To rationalize that, I'd have to multiply the top and bottom by those 5 missing groups. I don't want to do that. But what I can do is I can break 81 down. Remember, 81 is really 3 to the 4th power. So to rationalize, I need 6. I already have 4 of them, which means I am missing 2. This time, my 2 on the numerator is outside the radical, so it stays outside. And then I have the 6th root of 3 squared. I needed 6. I had 4. I added 2 more. So now I have that perfect group. Now, originally I would want to go 6th root of 9, but that's not going to work. This is 6 and this is 2. Those are going to simplify. Remember that that just represents a fraction. They're both divisible by 2. So that becomes the cube root of 3 all over 3. Last one in this section. I look here. I am going to rationalize. There are a couple different ways in which you can rationalize this. But if I were to approach this problem, I would first notice that these have the same base. So this is 5 to the 1/3. This is 5 to the 1/2. If I do my subtraction 1/3 minus 1/2, I get a negative exponent. So if I do my who wins rule, it's 1 over 5 to the 1/2 minus 1/3, which gives me 1 over 5 to the 1/6 power. So when I rewrite that, that's the 6th root of 5. Now I can start. I need 6 and I have 1. So I multiply the top and bottom by the remaining missing 5 that I need to finish the group. So on top, we have the 6th root of 5 to the 5th power. Well, 5 to the 5th power is 3,125. I needed 6. I only had 1. I finished the group with those 5 that I rationalized with, which means on the outside, I now have 5. Okay, as we turn over to the back side here, we are still rationalizing, but we are rationalizing with the conjugates. We have done this before. So to do this, all I'm going to do is change the plus to a minus. So to rationalize, I multiply top and bottom by 5 minus root 3, 5 minus root 3, top and bottom. So on top, 1 times 5 is 5. 1 times a negative root 3 is a negative root 3. On the bottom, we've got 5 times 5, 25, minus 5 root 3, plus 5 root 3. Remember, outside numbers together, inside numbers together. Root 3 times a negative root 3 is a negative root 9. Well, the square root of 9 is just 3. That was the whole point of the conjugate, was to get those middle terms to be the same. So it is 5 minus the square root of 3. 25 minus 3 is going to be 22. So remember, the conjugate is exactly what you have on the bottom. All you do is change the symbol. So for number 2, we multiply the top and bottom by 3 plus root 2. Go ahead and distribute. 5 times 3 is 15 plus 5 root 2. The bottom, 3 times 3 is 9 plus 3 root 2. We distribute the negative root 2, giving me negative 3 root 2 and minus 2, because root 2 times root 2 is just 2. Those middle terms cancel. Again, that's the point of multiplying by the conjugate. We end up with 9 minus 2, which is 5. What am I talking about? 9 minus 2 is not 5, that is 7. I was going to say we have to reduce our fraction down, but we don't. If this was 5, then these 3 numbers would have all been divisible by 5, and I would divide and simplify by 5. Okay, putting this all together. Just remember that your final answers must be written in simplified radical form. So you look at what property you have. Here, what do we have that's the same? Is I have the same base. When I'm multiplying like bases, I am adding the exponents. 3/4 and 5/4 is going to be 8/4. Well, that's just 3 squared. And guess what? 3 squared is just 9. Number 2, what do I have? I have, again, the same base. This time I'm dividing those like bases, which means I subtract the exponents. Just don't forget that on top, this is a 5. That's 5 to the 1st power. So this is 1 minus 1/5, which is 5 to the 4/5, giving me the 5th root of 5 to the 4th power. With variable bases, I didn't have to worry about this. I would just leave it as is, but this is a number, so you want to keep going. Since I can't pull any groups out, I go ahead in my calculator, I type in 5 to the 4th, and I get 625. Number 3, this one's a little hidden. What they have in common is that they both have the 1/4 power. So that's 3 times 2 to the 1/4 raised to the third. So that's really 6 to the 1/4. This is a power to a power, so we multiply, which gives us 3/4, which is the 4th root of 6 to the 3rd power. Again, I need 4. I only have 3. So I go ahead and take that one extra step to the 216 on the inside. I evaluate that 6 to the 3rd power. Number 4, we see these negative exponents. Negative exponents means reciprocal, so I move it back to the top of the fraction, giving me the cube, oops, I said it, didn't write it, the cube root of 6 to the 1st power. So all those exponent rules are coming into play. We look at number 5. What do they have in common? They all have the 1/3 power. So this is 5 times 4 divided by 2 to the 1/3. 5 times 4 is 20 divided by 2. 10 to the 1/3, giving me the cube root of 10. If it's a fractional exponent, then you have a radical. For number 6, they don't all have the same exponent. They don't even have the same base either. But if I look a little bit closer, right now they don't all have the same base, but they can. Remember, this is the one that we keep on starring because this is going to be that hard assessment question. So this one doesn't change, but 9 is really 3 squared. 27 is really 3 cubed. So I'm replacing the 9, I'm replacing the 27. Once I do that, I now have a power to a power, which means I'm multiplying. 2 times 2 is 4 divided by 3. On the bottom, 3 times 1/5 is 3/5. Now they all have the same base. So on top, I'm multiplying like bases, which means I'm adding the exponents. When I add those exponents, I end up with 25/12. Now that I have the same base that I'm dividing, I'm going to subtract the exponents. 25/12 minus 3/5 is 3 to the 89/60, giving me radical form. I need 60, I have 89. I can bring one group out. When I bring that one group out, I am left with 29 on the, 29 on the inside. One group of 60, I take 60 from 89, and I have 29 left. Now, we've been talking about how we multiply this out, and we normally do, but if you go into your calculator and you do 3 to the 29th power, it's this obnoxiously large number. So we're going to leave it as 3 to the 29th power. All right, number 7, they both have 1/2 power. So I have 15 divided by 5 to that 1/2 power. 15 divided by 5 is 3 to the 1/2 power. Raised to the 3rd. We have a power to a power, so we multiply. 1 times 3 is 3 divided by 2, which is 3/2. We go to radical form. I need 2, I have 3. I get to bring one group out, and there is one left over on the inside. All right, last section. We are almost done here. Adding and subtracting radicals. Remember, it has to be like terms. This is what's making it a like term. They are like terms, so I can go ahead and put them together. I have 5 here. It's not written, but I know it. It means that there's 1 there. 5 plus 1 is 6, 8th root of 2. Here I'm subtracting. It's not obvious, but this tells me that I have like terms already. 7 minus 9 is a -2. 3 to the 1/3 power, but we always write our answers in radical form, right? So this is a -2 cube root of 3. So adding, subtracting, you must have like terms. Like terms means same root, same number underneath the root. All right, now that is it. Have a fantastic day.